Okay, then good morning. Welcome to the session today. So I think this is where we somehow stopped on Wednesday when I explained the problem of every simulation, that you have this garbage in, garbage out principle, right? The computer is just a tool. You have to use the tool correctly. You have to give your model correctly, and then the computer will do something and will give you some result, and you have to interpret the result correctly. And yeah, so the software that we will be using today is this LTspice. I've seen that most of you are using your own computers, which is, I think, a good idea, because then once you have software installed on your own computer, you can also use it there. And if you have not yet downloaded it, then please just download it from this website. And it's free, and you can use it free of charge even for commercial projects. Okay, so then maybe some quick rules for the software. If you want to give numbers into the software, for example, to say how large a resistor is, or how large some inductor is, or whatever, you can use integer numbers. So if we have a 1 kilo ohm resistor, let's say, with 1000 ohm, you can say, okay, 1000 is of course 1000 ohm. Then, as usual in software, if you want to give fractions, you need to use a dot as a decimal separator or a point. So 1000.0 is the same as 1000. Don't use a comma won't work. You can also use the scientific notation. So 1e3 means like 10 to the power of 3. And yeah, so also 1.0 times 10 to the power of 3 will also give you the same result. And then LTspice also uses the SI prefixes. So 1K is like 1 kilo is also 1 kilo ohm. 1K0 would be 1.0 kilo ohm. As you can see, I've written a capital K here. Usually the K for the kilo ohm or kilogram or whatever would be a lowercase k. And so I've written this a bit on purpose, because LTspice won't take care of if it's lowercase or uppercase. So if you write 1M, because you want to have 1 mega ohm, so 1M is a milli. If you want to have mega, you need to write MEG, because it won't take care if it's a lowercase or uppercase m. So this is a typical failure. If you want to, let's say, have 1 M for a mega ohm, it will be a milli ohm instead, a totally different value. The same is if you write for a capacitor that has 1 farad, if you write 1F, it will be 1 femtofarad, which is 10 to the power of minus 12 or 15 or something very, very small. So if you want to have 1 farad, just write 1, right? The software won't take care about what is the real unit at the end. And in newer versions, you can also write the mu character for a micro henry or micro ohm or whatever. In older versions, this won't work. In older versions, you would just write a U for the micro. Okay, so I think that should be enough for the beginning. So my idea was to start with very simple examples, and then we will try to make them more complicated. And I think the easiest thing that we can do is we have a source and we have a resistor, so just a voltage source and a resistor in a series circuit, or I mean in this case it would also be a parallel circuit. And then this here means we will calculate a DC operating point. So just a very simple thing, yeah, where we have DC voltage, DC current, and so on. Okay, so I will try to find the LTspice on my computer, which should be here. And so once you install it and once you run it, it should look like this. This is the, let's say, the newer version. I think I also have the older version somewhere in my computer. At the end, they have the very same functionality. This just looks a little bit different, let's say. And if you want to start, the first button that you would like to push is this one here for a new schematic. So the one with the plus opens up a new schematic, and then you get a gray background. And then there are lots of buttons here on the top. And so there is one button which is new in this new graphical user interface for the voltage source. It was not there in the older version. There it was always a bit difficult to find the voltage source, but here it's quite easy. So we have the voltage source. You just click on this and you get the voltage source, and you can place it wherever you like. And there are, so I will click here, and you could also place the second one. If you look to the lower left button on the screen, there are also some hints. So if you press Ctrl R on the keyboard, you can rotate this like this. And if you press Ctrl E, you can mirror. But I mean, mirroring for the voltage source does not really do something meaningful because it's a bipole element, just two terminals. If you have a transistor, for example, then of course mirroring does something useful. Okay, and so if you don't want to have another voltage source, which we don't want to like here, you press Escape on the keyboard and then you will get out of this mode. Okay, so now we have placed a voltage source. So what is missing? What do we need for our circuit? If we want to draw this, we need to have a resistor. This is the... By the way, in Spain, do you use this symbol for a resistor, or do you use the other symbol for the resistor, this one here? This one, or both? Okay, because in Germany, this would be more common to use as a resistor. But of course, we also know that this one here exists. So I would say this is more the American symbol for resistor. So we can maybe place it somewhere here. And once again, if you press Escape on the keyboard, then you get out of this resistor mode. Okay, so now we should have a voltage source and a resistor. And the next thing that we need is we need to wire them together. And so the wire tool is here on top, or you could also press W on the keyboard, and then you get like this crosshair symbol. And yeah, you can start to click on one terminal, and then it will draw a wire. And if you want to have like a corner of the wire, you click once again, you get the corner. And then we maybe want to have another corner here and connect this. And then you can see if it's properly connected, then let's say this soldering pad, this terminal will disappear because now it's properly connected. And then, okay, I need to have a second wire going back because we know current always wants to go in circles. And so we have a wire for the forward current, we have a wire for the return current. When you have by accident drawn a wire at the wrong position and want to delete this, then press delete on the keyboard. Then the mouse will turn into a small scissors symbol, and with the scissors you can then remove or cut wires that you don't like to have in your schematic anymore. Okay, so now we have a voltage source, we have a resistor, we have the connecting wires. Now our elements, our symbols need to have the proper quantities. And you can define and set the quantities if you take the alternative mouse button, so usually the right mouse button, if you have a right-hand mouse, and click on the symbol, and then you can set the values. So here we can set the DC value. I would suggest to maybe set the DC value to 12 volts because this would be the voltage in the automotive low voltage system. So we have a 12 volt source. And we can then also set the resistance, I don't know, for example, to 1 ohm. And if we do so, if we have a 12-volt source and a 1 ohm resistor. Which current should we get at the end in our circuit? Also 12 ampere, right? Okay, so we have our symbols, they have values, they are connected to each other. Now we can maybe try to start the simulation, and this works with this green or greenish button here that runs the simulation. And before we can run the simulation, we need to say, okay, what type of simulation do we would like to have? And as you can see, there are many options. So we can do a transient analysis, which means an analysis in time domain. So we get the result as a function of time. This is what we will do later. AC analysis is really the stuff that you maybe do in the second semester of electrical engineering, calculating with complex phasors in the frequency domain. So this is what happens here, and we can have a DC sweep where we change, so we change the value of a DC source. Then there's noise analysis, okay, DC transfer, some transient frequency response. The thing that we would like to have now is this, as mentioned on my slides, if I go quickly back to my slides, this DC operating point. And so we select this DC operating point, and then it says OP, and it does the simulation already. And so we see that we get the result now here as kind of a table, and we get the voltages, or not really voltages, I will explain in a second what this means here, and we get currents. And usually in older versions of SPICE and other versions of SPICE and also older versions of LTspice, this would not have worked. So because I'm more used to the older version, I've just installed the newer version today, I'm quite surprised that it works. Because what is missing? There is no ground, right? What happens in the background if this software simulates and calculates the circuit, it is doing nodal analysis or modified nodal analysis. And usually the very first step, if you do nodal analysis, is you select or you set a reference node or you select a ground node. And this ground node is here. And so if we, or maybe I will place this ground node in a second. Once again, if you take a look at this lower left corner here, this is always quite useful on the screen. And if you hover the mouse over here, then you see, okay, it automatically numbered the nodes, and it says, okay, this is node 001, and this is the node 002. So because I've drawn the wire here first, this was labeled as the first node, this was labeled as the second node, and you can also see, okay, here we have minus 12 ampere of current, here we have plus 12 ampere of current, and we have a certain power dissipated.
Can you recover the operating point without simulating again? Because I have closed the window. So
Okay, yeah, if you just click once again on run, then we should get the result once again. Okay, and as said, usually this should not have worked in older simulations or in older versions. So I will try to find, I think, no, this is duplicate, this is stretch.
He's using ground, maybe where?
Yeah,
The negative part of the source, voltage source.
exactly. So I'm looking for the hand symbol here in this, but okay, maybe I can. No, I cannot pick it up with my hand to move this around. Okay, but anyhow, I will take the ground and place the ground somewhere here at the bottom of the circuit and connect the ground. And so now it says this is the ground of my circuit. This is still the first node. And once again, if I start the simulation, and now it's taking quite a time to run the simulation. which is kind of strange. Okay, but maybe my computer is just super slow at the moment because it's sweating. Yeah, but we've turned on the AC in the room. That's why it's maybe also quite loud, and there's some other fan of a network device blowing here all the time. Okay, but now we can see, okay, we just get 1 voltage anymore. And this is, as said, it's not really, I mean, it's labeled here as a voltage, but to be honest, from my point of view, as a sincere electrical engineer, it's not really a voltage, it's a potential. It's the potential of this node against the ground node, or it's the voltage between this node and the ground node. So the voltages that you see here are not really voltages, or usually not voltages across some element. It's always the voltage between a certain node and the ground node. It's like a nodal voltage. It's the result of this nodal voltage analysis that is there in the background. And I mean, in this case, if we take the voltage from here to the ground node, of course, it's the same voltage as across the resistor, which is 12 volts, of course, the voltage set here by our source. And then, as we discussed before, if we have 12 volts, if we have a 1 ohm resistor, we should get 12 ampere of current. And we can see here, okay, we get 12 ampere of current through the resistor. Yeah, why do we get minus 12 ampere of current through the voltage source? Yeah, so here it's meant that positive current is going in this direction, is going down also through this voltage source from the plus node to the minus node. But in reality, the current is going like this way, like clockwise, right? And this current here would be counted counterclockwise in the opposite direction, and that's why it's negative. And yeah, we don't really see at the, or I mean, we have just arbitrarily placed this resistor, and luckily it was placed in a way that here the current is counted downwards through our resistor. To be honest, I don't really find the button. Let me close this here. Let's see if my computer is really slow. I'm not sure why. Okay. Let me see if I can, if I find the proper button. Here's something like move. So if I take this move tool and click on the resistor, and so now the resistor from the circuit, I'll press the resistor back into my circuit. Oops. Left. Okay, or, and if I now resimulate, yeah, I've turned the resistor by 180 degrees, now I should also get a negative current through this resistor. I'm not sure why the simulation takes maybe also some time to try this out on your computer. The resistor, the thing, right? The resistor looks the same as before. You cannot see it at the moment, still negative current through the resistor. Some result. Yeah, so now you can see now also the current through the resistor is counted negative because I've rotated the resistor. Still the resistor looks the same as before. So I will maybe move the resistor out of my circuit or rotate it once again by 180 degrees, try to put it back in, and then of course the current should be positive once again. Okay, so do you have questions, or which questions do you have until now?
We have some discussion.
Some discussion, that's good.
Yes. Also in pitfalls, you rotate the resistor, the current is negative.
The current gets negative,
so
yeah.
This is to interpret the results, because
yeah.
Why you have to know that you have a
we will see in a second. So if I go to the next slide, you can see not so much changes because we take the very same circuit, and now we will do transient analysis.
No, but it is possible to know how is the sense of the resistor if you go to the text by.
Yeah. Okay. Yeah.
Starting with Spice, I did
That's a good comment.
Yeah. This is the way in which you can show.
Yeah.
It has to do with the numerical resolution of the circuit, or?
So I'm not sure if I can show this here. So usually what happens is that so here for view there is some option that says update and view the SPICE netlist. And if we open up this netlist, okay, there's not so much there now in this netlist. Okay, because I think by accident I just created a new circuit. Okay, here's my original circuit. So now if I update and view the SPICE netlist, now we can see, okay, there is a voltage source connected between our automatically numbered node and the ground node. And then there's the resistor, which is also between this node. And that's why the resistor is, let's say, pointing downwards. This is here in this DC operating point mode, it's the only option how you can see it. As you said, by looking at this netlist. So in the background, what still happens in this LTspice, I mean, it's just a graphical user interface. From the graphical user interface, it will create such a netlist, and then this netlist is used to run the solver.
I know that the LTspice and pitfalls do that.
Yes.
But physically, I don't understand why they don't represent the current from the positive to the negative point, because
yeah,
it's the current is always
yeah. It's
I don't understand.
Yeah, we will see in a second. So now if we take the very same circuit and now go from DC operating point to this transient analysis, which means we will simulate our circuit in time domain, get the result as a function of time. So now this was the setting to do the operation, DC operating point. If you once again click on this with the alternative mouse button, with the right mouse button, or if you have a right-hand mouse, now we switch to transient. And then it asks us for several settings, and it asks, for example, what should be the stop time of our simulation, how long we would like to simulate. And so I will do something like 100 milliseconds, maybe, or you could also do 1 second, whatever you like. I will do 100 milliseconds and just press OK. The rest we can leave as it is for a moment. And so now this is somehow disabled, this setting, and now this is the active setting that we will do a transient analysis for 100 milliseconds. And so I will run once again. And now some empty diagram will open up. And there's a question.
Where click?
Say again?
Where click?
How to set this? Click with the other mouse button.
When you finish the configuration, I put trans 110 in
Yeah, so I think you can also, you can go to simulate and say settings. No, not settings. Simulate and configure analysis. And then you get to this. And before we use this mode, now we're using this mode here, the transient mode. And I mean, we still have a DC source that does not change over time. So it does not matter if you simulate 1 microsecond, a millisecond, a second, whatever. another hint is you can zoom in and out here with the mouse. You can move this circuit around with the mouse button. If you are in a strange zoom setting and let's say want to go back to the home screen, that the circuit nicely fits your screen, just press the space button on the keyboard and the space button will do a nice zoom. Okay, so if we run the simulation in this transient mode, now something interesting happens. If you hover the mouse over your circuit, now you see if we are above some element, the mouse turns into a small current probe. Remember the current probe that I had on Wednesday for my measurements? I think it must be somewhere here in the slides. So on Wednesday I was using this current probe here from Chauvin-Arnoux to measure the current. And so here now also the mouse turns into the small current probe. And now you can see that the current through the source would be measured in the direction down, and the current through the resistor would be also measured in the direction down. If I take the resistor, once again cut it out of the circuit, rotate it by 180 degrees, put it back in, resimulate. Now you can see that the current would be also measured in the upward direction. So now here you can see what is the direction of the resistor by taking a look at this current probe. So now you can see, okay, we are measuring, let's say, the upward current. If I take the resistor, rotate it once again, put it back in, now we measure the downward current. Okay, so this is how to measure current, and if you are above a node or on a wire, then you can see the mouse cursor turns into a small voltage probe. Like the voltage probe, this is looking pretty similar to the voltage probe that I used on Wednesday, right? The red voltage probe is the same red voltage probe as the small probe here. Okay, so now if we take a look at the current, if I click the button, what should I get? What would you expect? We have a 12 volt DC source, we have a 1 ohm resistor, the source does not change over time. So we get a flat, we should get a flat curve around 12 or at 12, exactly 12 ampere, which we get. Okay. Everyone arrived at this point? Yeah, we could also probe the voltage there, and now we get two axes. We get an axis for the voltage, we get an axis for the current, and of course, I mean, because of the 1 ohm resistor, they are both 12 volt, 12 ampere, very same line now on top of each other. Okay, so then I will go back to my slides, take a look at what we did so far. We did transient analysis with the resistor. So in our motor that we would like to model, we not only have a resistor, we also have some inductor. So the next idea would be, okay, let's replace the resistor by some inductor to check what it does. And of course, we will still stick to this transient analysis. Oops. And so let's replace the resistor by some inductor. And so I push the delete button on the keyboard, then the mouse turns into the small scissors, so I can remove the resistor. And then the inductor is this symbol, which is also the symbol that more or less we would use in Germany for some inductor. This is also more or less the American symbol. Place the inductor back in. And now, of course, the inductor also needs to have some value. And once again, if you click the alternative mouse button, the right mouse button on a right-hand mouse, we can set a value. And I would suggest to, for example, remember what we calculated on on Wednesday approximately for the inductance of the motor something like a millihenry, right? Because we had this time constant of 1 millisecond that we measured approximately in this. I have this diagram here open somewhere, right? This was the transient that we measured when switching on the blocked motor, and this time range here was in milliseconds, 2 milliseconds per division. So yeah, the time constant could be something like a millisecond. And we had 1 ohm approximately of resistance, so 1 millihenry should be fine. Okay, so we have 12 volts. We simulate over 100 milliseconds. And so now if I run the simulation once again, it's from my point of view always a good idea to think about what should happen. What should happen if I have a constant DC source, and with the constant DC source I power an inductor? What should the current do? Yeah, it should, because if you remember what we discussed on Wednesday, also for the inductor, I need to go way back in my slides, somewhere to the beginning where we discussed the inductance here. Yeah, so we have a constant voltage, we have a constant inductance, then we should get a constant time derivative of the current. So the current should just increase linearly up to infinity. If we wait infinitely long, current should go to infinity. Okay, so if we try this in our simulator and click run, and now the current has gone from the diagram here because it was the current through the resistor. We don't have a resistor anymore. Now we have some inductor. So I need to press look at this current here once again. Okay, then what do we see? We don't see a linearly increasing current. We see a constant current, and we see a constant current of 12 kiloampere. Okay, so going back to my slides, we have now found a very nice example of this one here, of this principle, garbage in, garbage out, right? The simulator has solved the problem correctly, we've just used it wrong. Okay, so yeah, why do we get the constant current? And why 12 kiloampere? Anyone some idea? Yeah, because it's not some ideal coil. Once again, if we click on this with the alternative mouse button, then it says, okay, there's a series resistance that defaults to 1 milliohm. So inside our inductor, there's an internal resistance of 1 milliohm. If we have 12 volt as a source voltage, if we have 1 milliohm as a resistance, we will get 12 kiloampere of current. This is the 12 kiloampere that we get here. So of course, what we could do is we could set this to 0. I'm not sure what happens now. Hopefully it won't crash. So run it once again. Okay, then it says, I'm sorry, this won't work. I cannot. We have a voltage source and an inductor in parallel, and we have some overdefined circuit matrix, and this won't work. You need to add some series resistance. I mean, by the rules of circuit calculation, this should work, but it does not work in the simulator. Okay, so we need to delete the 0 here once again. Then if we do this, then okay, of course we are back with our settings that we had before. So any other ideas what we could change in the settings? Say again? Yeah, Yeah. So the problem is that our source it's still a DC source. It's already switched on all the time. So I think what we could do is we could change the source. I will do another thing. I will go back to the simulation settings. So once again, click with the alternative mouse button on this transient setting here to open up this view that we had once again, where we said that we, for example, want to simulate for 100 milliseconds. And there is, the last setting here says, skip the initial operating point solution, because what LTspice does in the background, it already tries to find like the steady state of our circuit. What would happen if the source is switched on already for an infinite amount of time? And so if we hit this button, just this, so this tiny setting should make a huge difference. And now you see that something is added here, and the abbreviation UIC, which stands for use initial condition. I mean, at the end, what we do is we somehow solve some differential equation, and the solution of a differential equation depends on the initial condition. If you have followed your mathematics classes about differential equations, right? And for getting a well-defined solution of a differential equation, we need to have some initial condition. Okay, and so now if we rerun with this setting, then we can see, okay, very nice. We get some increasing current. And yeah, so over the 100 milliseconds, we should get to 1.12, 1.2 kiloampere, and we don't really reach the 1.2 kiloampere because of the 1 milliohm resistance. I'm not sure if we now can set the resistance to 0, but okay, this once again won't work anymore. Yeah, and so because of this resistance that is not perfectly 0, it won't be a perfect curve, a perfect linear curve, especially if I go up for longer times. And you can see that it's a little bit bending down. Yes?
I have tried to write a negative series resistance,
Uh-huh.
and something happens. If you want to
I maybe want to change to see a negative series resistance.
-1 milli,
Minus 1 milli, okay. I've never tried negative. Okay, and then of course something very interesting happens, that the current would increase even more. I'm not sure if this has a useful physical meaning, but of course you can try. I'm not sure if this would work in the older version, but yeah. Now once again, according to the equation that we discussed, we should expect a perfect linear increase going to infinity, and we don't see a perfect linear increase. We see something like this exponential increase going to this fixed value of 12 kiloampere because of the 1 milliohm resistance there. So, but for small times, if we don't simulate 10 seconds, but just 10 milliseconds, for example, then it looks almost perfectly linear. So this is what we would expect. Okay. Questions so far? No questions? Okay. Then we can continue. So this is what we have done now. Just the inductor. So now we can have almost, let's say, the perfect electrical part of our DC motor model, the source and at least the resistance of the winding and the inductance of the winding, and simulate this. And I mean, there should not such a big surprise now. If we add some resistor, and I will rotate the resistor, maybe zoom out of the circuit a little bit. So remember, if we just took the resistor, current was pointing downwards. If I rotate, it will rotate clockwise. So now the current will look to the left, upwards, and now to the right. This is the direction that I maybe want to have, the same direction as the current through the inductor. And I will, maybe to make this larger, I will tile the windows vertically. So now I will set the resistance, yeah, to, I have the table here somewhere from Wednesday, and so this is where Alejandro helped me to collect these values, and I have watched or looked at the video recording once again, because I think Alejandro missed some value in between and we did the measurement later on, and so from the recording I used the values, and still it's not looking perfectly nice, but I get a more straight curve here, right? And so from when the motor was not running, which were the first two cases, oh, and I think this should be also 0 now. Okay, I cannot change the values here. I need to change this later on. But from the measurements where the motor was not running, we could get the resistance, and the resistance was maybe something like 1.1 ohm. So, okay, let's use 1.1 ohm here for the resistance and the 1 millihenry for our motor. And then remember, I did this measurement when switching on the blocked motor, and I think I had something like 4 volts at the source. And then we would get like this, something between 3 and 4 ampere of current. And this was also happening here in the range of 20 milliseconds, right? So from minus 2 milliseconds to 80 milliseconds, it's 10 divisions, 2 milliseconds per division, 20 milliseconds. So if we set this to 20 milliseconds, with a 1.1 ohm resistor and an approximately 1 millihenry of inductor, and now not with a 12 volt source, but with a 4 volt source, it should be pretty the same settings of my blocked motor. There's no counter electromotive force. We just have the resistance and the inductance of the winding of the blocked motor. So if I now hit the simulate button, I should get pretty the same result that we got here in the measurement. And so if I do so, well, you can see it's working quite nice. I can try to put this in on the same window. So I will go to tile horizontally, and then maybe try to find this here and make this a bit smaller, and maybe try to put this on the very same screen, and then maybe zoom in a bit. And then you can see it's looking pretty nice. It's the same time range, it's about the same current range. So of course it would be much better now to, I don't know, not have only saved a picture of the results, but really have to save the values and then maybe export the values from LTspice, import both into MATLAB, and then do the comparison there. Next time when I do this, I will maybe export the values from the oscilloscope and somehow try to import them into LTspice so that one could have a direct comparison there. But I think at the end it's not looking too bad. Yeah? So we get a quite nice agreement between the real measurement of the motor and this very, very simple model of the blocked motor that just consists of the winding resistance and the winding inductance and our DC source. Okay, which questions do you have so far? There is one.
How calculate the inductor?
How to get the inductance of the motor? So as discussed on Wednesday, let me go back to the corresponding slide, which was this one here. So if we have the blocked motor, as said, there is no counter electromotive force because we have no speed. So we really just have our voltage source, the motor resistance, the motor inductance. And we can set up Kirchhoff's voltage law for the circuit, which would look like this, that the source voltage needs to go into the motor resistance and Ohm's law into the law of induction. And then this is your basic differential equation, first order linear inhomogeneous differential equation, the kind of simplest differential equation that you can solve in mathematics. Okay, it would be even simpler if the source voltage would be 0, then it would be the homogeneous one, but and the solution of this is this increasing exponential function. And one step in the solution is that the time constant of this exponential function depends on the motor inductance and the motor resistance. And if we know the motor resistance already, and if we determine the time function, and then we can calculate the motor inductance. And determining the time function would work like that in this diagram. I'm not sure if I can try to show it and explain it. So I will use Microsoft Paint, which is probably the simplest program that you can use for this application. So there is Paint. And my computer is really slow, but it doesn't matter. Okay, and then I will copy this diagram that we measured, and then Paint will hopefully open up. Yeah, and so then the idea, there it is. Okay, so let's insert this here. And now what I can do in Paint is I can draw lines. So I will use red, which is nicely visible, and I will use a bit of a thinner line. So this is the point where we start, right? This is the point where we switch on. And maybe use a different color. And this is our steady state solution. So if I draw a parallel line from the steady state, this would be our steady state. And now let's use another color, maybe green. And now if I start here at this point and draw a tangent line to the curve. Oh, I wanted to have, now maybe let's use red. So if I draw a line that is a tangent to my curve. So yeah, now it would be too steep. Now it would be too shallow. Now it has, let's say, the perfect slope to get a good fit here at the beginning. And now where this tangent hits the steady state curve. So the distance from here to here, this distance, this is one time constant. And then you can see if one division is 2 milliseconds, this is maybe half a division, so it's, yeah, the time constant, the measured time constant is a bit less than 1 millisecond. And so if we take a bit less than 1 millisecond, multiply it with this rotor or motor resistance that is a bit more than 1 ohm, then we get approximately 1 millihenry. I'm sorry, I'm always confusing the milli and the micro there. Yeah, and that's why we get this nice fit. But we can check if we, so the time constant is the inductance divided by the resistance. If we take more inductance, so if I not take 1 milli but 2 milli, then everything should happen slower. So if I simulate, we should reach the steady state later. my computer is slow. So now it's doing the job. And now we should see after some time, maybe, hopefully. Okay. It's still calculating and plotting. That the curve is not that steep anymore, but now that the transient takes more time. And so, I mean, at the end, you could just try to fit the motor inductance to your measured curve without calculating the time constant. But in this case, it's quite okay to calculate the time constant, I would guess. Okay, so I will go back to the 1 milli. Maybe resimulate again in the background and then maybe change over to my slide. Okay, this fits. Then go forward in the slides to my simulation models. The next thing that we could do is, so now we could try to have also the mechanical part of the motor. So just to give you the idea. And for the mechanical part, we needed to have this controlled source, a controlled voltage source that would give us a voltage that corresponds to the torque generated by the motor. And then in this circuit, we will have a current. The current corresponds to the speed of the motor. And then we might have a resistance here that accounts for the friction inside the motor, for the viscous friction. And just to give you an idea of how these controlled sources work, let's maybe have one of these controlled sources. Okay, so I will go back to LTspice. I will move this also over to the left a little bit. My computer is still working in the background. Okay, this was too much to the left. Okay, maybe it's also too hot for the computer. Okay, and so now you can see, okay, there is no symbol for these controlled sources. So we have to go to Edit. And then there should be an option that is called Component. And if you click on this, there will be a huge list and library of all possible components that are there in this circuit simulator. And you can see that there are also analog to digital converters, there are comparators, filter components, operational amplifiers, switches, all kind of stuff. And I mean, this is also the reason why LTspice gives out this software, because you would find all the components that you can buy from linear technology, from analog devices. And here there is an element called H, and H is written here, it's a linear current dependent voltage source. So it's a voltage source, it's a controlled voltage source that depends on the current at the different part of the circuit. And in SPICE, they are called H sources. And if you remember Wednesday, I won't go back to the corresponding slide, but they are also called this H, an H source or an H voltage. So H is the thing that we would like to have, so we will place it. I will place it somewhere here. It looks like a usual voltage source, it just got the H there. And then I would take another resistor, let it just point downwards, take the wire tool, wire everything together. And I think I will also have a second ground symbol here for the second circuit. Okay, and now the resistance here also needs to have the value that we have for the resistance. If I go back to the table that I have opened up in my browser, with the formulas given in the slides, I've tried to calculate this resistance there for the friction with the formula provided in the slides, and that you can see that no matter which source voltage and so on we use, we don't get a really clear value. So I will use the last one here, something quite small. But at the end, it does not really matter. So I don't know, maybe use 0.15, 0.2, whatever. And then we need to have this factor that a current here will create a certain torque. And this was called a K factor, a trans resistance. And I've also tried to calculate this. This is this column here in my slides. And here you can see that we get a more or less clear value, especially for the higher voltages, which is at around 0.88, 0.9, something like this. And so if you click on this, then it's getting a bit difficult because, yeah, I think here it's not very user-friendly how to set these controlled sources. You just see, okay, you can set two values, a value and a second value. And so I will click once again on cancel, and because I also don't remember correctly, take a look at the help. So let's just open up the help, the LTspice help, and there should be a menu that corresponds, oh, interestingly, it does not, it opens the help in a browser and not some, this is different than what I was used to. But okay, anyhow, it opens in the browser, and there's some help for the circuit elements. And inside these circuit elements, we should somewhere find H, the current dependent voltage source. And then we can see how this works. So the source is connected to between two nodes, and then there are these two values. And the first value is the name of another voltage source. And then the second value is this trans resistance, or this K factor. And so the name of the voltage source means like a current sensor, right? If we have a current dependent voltage source, we need to measure the current somewhere else in the circuit. And measuring the current works with voltage sources. So we can just use this voltage source as a sensor, and we will take the current through this voltage source and then put it into this source here. And as discussed, the current here is pointing in the wrong direction, so then our trans resistance, the K factor, needs to be negative at the end. Okay, so I will just change this value to V1 because this is the name of this source. And then the second value is this trans resistance, and I will set it to the value that we got from the table, 0.89, but with a minus because of the different direction. And so the first value is V1 because this is the name of the source that we sense the current here. And the second value is the trans resistance. Once again, this is what I got from my table here, 0.89, calculated from the values that I measured with the support of Alejandro. And then the minus is because we want to have positive current pointing upwards, but this is measuring current pointing downwards. This is why we have the minus. Okay, and so now here nothing really should happen because there is no, we would need to have a second source for the back reaction, but we should get something here. And we can just try it out if we get something on this side. So if I run, okay, I think it already ran. And if I look at the current here, okay, then I get a similar current on the other side of the circuit, which should be the case because I've now just copied the current from this side to another circuit, and we get the same thing, right? Just that the current here is yeah, interestingly, why is it larger?
You have gain.
Yeah, but the gain is minus 0.8.
But the resistor is lower. It's 0.15.
Ah, but the resistance is lower, of course, and that's sure, okay. And that's why we have a gain. If we set the resistance of 1, very good point, then we should get the let's say the same. If we set our transfer value to 1, we should get the very same current. Okay, and of course, if we set this gain to something smaller, 0.89, let's just double check, then the current in the new circuit is smaller because of this 0.89 factor. And if we make this resistance smaller than 1, of course, then we get more current. Makes perfect sense. Okay, excellent. Sure.
Are you measuring the data?
Say again?
Where you are measuring
The current just by clicking on this resistor once again with this small current probe that we have there. Yeah, sure, you're welcome. Okay, so right now we could continue, have a second trans resistance here, and yeah, and maybe take a look at the back reaction. So maybe let's do this. Why not? I think we still have some time. So I will maybe move this up a little bit, use the other tool here, which is the stretch mode, and stretch this down a little bit so that I have more space here for another controlled source. And we'll use once again this H source component, place it here, and I will name this H EMF for the counter electromotive force, and I will maybe rename this to H torque because this was the one creating the torque. Yeah, and so current would be also going downwards here. I'm not sure if I can use also this H source as a sensor, but we will see in a second. So if I take here H torque as the sensor, the current that is going through this source now should also control the source here on the other side. And I will take the very same value for this K factor, minus 3.89. And let's see what it does. And maybe tile the windows vertically once again, but I need to okay. Yeah. Then you can see, okay, now we get a little bit of this current overshooting effect that we had before, but not quite yet, because what is missing in our circuit? Or what is missing in the mechanical part of the motor to more capture the real behavior of the motor? Yeah, the inertia. We need to have another inductance here. And so let's place some inductance here. So once again, if I just take the usual thing, current should point out downwards. If I rotate once, current should point to the left, to the top, to the right, and place it here. Okay, and then the question is, what is the value of this inductor? And remember that we also did this measurement here where I switched off the idling motor. And then it took something like 100 milliseconds for the idling motor to stop. Yeah, and so there we also had some friction. We started with the 12 volts. It's a bit difficult to calculate what inductance we have now. But if we start with something in the millihenry range, once again, it should not be that wrong. So let's also maybe start with 10 milli or so. I'm not sure. So just as an explanation, maybe I will enlarge this a bit. Now we have the and I can also put labels here. So add some text. So now we have the electrical part of the motor, which is here, and we have the mechanical part of the motor, which is here. Right? This is our motor resistance, this or the coil resistance. This is the motor inductance. This is the inductance that we have for the inertia. And this is the resistance that we have for the friction of the motor, for the viscous friction. And we have a controlled source for the counter electromotive force. We have a source for the torque. And we have this, the source of our battery or whatever. And if I change this, I think I also need to change it here. Okay, I hope I have not changed too much and then it still runs. So if I run, and if we now once again take a look at this current through the motor, now we are somehow switching on the idling motor. And so then we see, okay, we get this nice overshooting of the current. Because at the beginning, right, the motor needs to start to rotate. We can also have a look at the current here, which is the speed of the motor, and we can see, okay, at the beginning, the motor does not rotate, then it speeds up. Because it's speeding up, it's creating this counter electromotive force. And this is acting against our initial current flow. And that's why we have this, let's say, this inrush current. And then the voltage, the current is somehow going down. And this is the same that I've also measured, or that we have measured on Wednesday, which was this diagram here. So I will once again try to get this on the very same screen here. And maybe zoom in a bit. And then we can see here we had 20 milliseconds per division. So the total range that we then simulated was 200 milliseconds. So I will go back to my simulator and change the time to 200 milliseconds from 20 to 200. And resimulate once again. Well, we can see, okay, it's looking pretty similar. Still, if we take a look at the axis here, the current went up to 10, almost to 10 ampere. In our simulation, we only go up to 3 point something ampere. What might be the cause for this? What might be the difference between this measurement and the simulation? If I remember correctly, probably you won't remember, for this measurement I've not used 4 volts of source voltage but 10 volts of source voltage. So with 10 volts instead of 4 volts, yeah, we also reach higher currents. And so the agreement between this blue curve here and this greenish curve here is quite good, I would say. Yeah? So here we almost reach 10 ampere. Here we don't. We have something like 8 ampere, and then current goes down to a little less than 2 ampere. Here we have a bit more than 2 ampere. Maybe we have too much friction in our motor. Maybe we should have a bit more of inertia. We can try. Yeah? So if we have a little less friction and maybe a bit more of inertia, maybe go from 10 to 20 if I resimulate. Okay, then it's maybe looking a bit more what we have here in the measurement. No, not too bad, right? At least we can nicely simulate this inrush current. Do you remember why do we get a smooth curve here in the simulation and why we have this noisy and rippled curve in the measurement? Yeah, this was because of the brushes, the back reaction or the influence of the brushes. And we don't have any brushes here in our model, so that's why there's no ripple there. Okay, I would guess this is looking quite nice. Yeah, and so the last thing that we can maybe try to do with our simple model here is to try to simulate this current voltage characteristic that I measured here with the support of Alejandro. So this was the steady state, no transient. And we changed the source voltage and looked at the current. So I hope, I've not tried before, that we can also try to do this here. So I will enlarge my circuit and we go back to the simulation settings. So use the alternative mouse button to click on the simulation setting or go to simulate and configure analysis. And then we want to have a DC sweep. So now we want to sweep this source here, which is called V battery. I still have it on my clipboard. This is the source that we would like to sweep, and we want to do a linear sweep. We want to start with a value of 0, we want to stop with a value of 12, and we maybe want to have an increment of 1, because these will be the very same settings that I had here in the table. Starting at 0, ending at 12, having steps of 1. Okay, and if we do so, we get another simulation command. Yeah, a DC sweep of this source going from 0 to 12 in steps of 1. And if I run, and if we now take a look at this curve here, yeah, then if I try to compare this on the very same slide, on the very same page, maybe I need to change the browser settings a little bit, or no, I think maybe I need to do it like this, tile vertically, and then maybe do the browser window like this, that I also switch this to this side. And then move over that I only see the diagram. Nah. Okay, there is the diagram. There it is. Okay, and we can see. Okay, it's not looking so similar. So what's the problem with my model now? Why did we had this step here where the current would increase more at the beginning, then the current would go down, and we had this less steep increase? And why do we, I mean, at the end we are ending with more or less the same value. Now my friction here is a bit small maybe. If I go back to 0.15, if I resimulate, then it's fitting better. Yeah? So here we end up with something like 1.8 ampere. Here we're ending up with something like 1.8 ampere, but we don't have this this bend in between. So why do we have the bend here, and why do we don't have the bend over there? And this is the all models are wrong, some models are useful. Yeah, what happened here is that for the first two values that we measured, the motor was not rotating. There was so much friction in the motor that the motor won't start. And in our model, we don't have this type of friction. This is a friction that is independent of the velocity, independent of the speed. It's this constant friction. And here we only have viscous friction. And now we would need to add some kind of friction that is independent of the velocity. We could try. So if I once again take this tool to stretch this down, and now if we add another voltage source that is opposing the torque, right? So this source does a current in this direction clockwise. This source would do a current in the other direction counterclockwise. And if I go back to my table, so I've tried to calculate this here. This would be this friction that is independent of the speed. And you can see, depending on what values we use, we get something like 1.5, 1.6. So if I have a source here that has 1.6 volts for, this is the source for constant friction. And if I rerun my model, okay, it does not do anything, yeah, because now the problem is, this will make the motor, this will also act like a torque, this will make the motor rotate in the opposite direction. It will not really stop the motor from rotating, it will make the motor rotate in the opposite direction. And so, okay, now we would need to have a controlled source that somehow measures the torque, and if the torque is bigger than the friction and so on, then this source should be switched on and off and so on. So now things are getting complicated, right? now things are getting complicated. And so there was a nice German TV series with a host that, and unfortunately, I think he already died. But it was quite popular in my youth, and he also did experiments, and he show how you could craft something and make something do it yourself and so on. And he always had this saying of, I have prepared something, right? When something was not working, he was saying, I have prepared something, and I have also prepared something. So the next step is, if you want to simulate the whole motor, if you open up this website in your browser. So I will show the link once again, but I will click on this for a second just to check if it works. But it should be, because it's loading something. Hopefully. I will go back to the link. I think it's loading. So if you go to this website, bit.ly, and then LTspice Badajoz, with the LT and the B in uppercase and everything else in lowercase, then you should go to this website that hopefully loads. And there should be several LTspice files. Yeah, so it says it's some public shared folder. And there should be, I don't know why it's taking that long, but maybe because my computer is slow. Yeah, I've also opened up the folder here on my computer already. Okay, and so there you find the slides. You would also find an older version of LTspice that you can just download and let's say run a computer where you don't have administrative rights. And then there are 4 models that I've also opened up here. So, and we can have a look at them. So, switch on the blocked motor, switch on the running motor, and switch off the running motor, and the characteristics of the running motor. And I mean, these are exactly the things that I have measured. So I will once again start with switching on off the blocked motor, which gave us, if you remember, this curve here where we also determined the time function. And computer is doing stuff, but not really responding. So no, maybe I will also leave this open. I think it's still opening. So you can download these files from there and also run it on your computer. And it's models, as said, that I have prepared in advance. Actually, this has also been a research project that we have done a couple of years ago with a big German car manufacturer. I wonder if it's opening. Or maybe I was thinking just to open it up here. I think my German computer can't handle the Spanish weather, but the AC is running pretty strong in this room. Okay, so let's see if it works if I try to move this over to here. Ah, now it opened up in the background. Okay. Okay, so you see the same model, a bit more sophisticated. It will hopefully enlarge, and then I can maybe also zoom in a bit if the computer is responding. So you can see that I have also a source, that we have the motor resistance and inductance. I have a source just as a sensor. And we have this back electromotive force. We have the torque, we have the inertia, and here I have a source that just does friction. And you can see here it's a quite complicated function that does exactly the thing what I have discussed, that it will switch off or switch on and off the source depending on the speed of the motor. So it will somehow measure the torque and the speed and so on and so on. And so now if we have a very big resistance on this side that would block the motor, and if we simulate and take a look at, okay, so it's now simulating, and then take a look at the current through the motor inductance. Once the schematic is opened up, we should see the curve that we all know already, this exponential increase of the current. And okay, I mean, in this case, as really nothing is going on this side of the circuit, it does not make a huge difference what type of friction and inertia and so we have, because this is not not doing anything. And you can see here I have a bit more of motor inductance, I have a bit more of motor resistance, I have a piecewise linear source, but we get the same curve. Here I've modeled it in a way that it does the same stuff as in the measurement, acting a bit like a trigger, right? So remember, this is the same thing that we did here. Okay, so this is looking good. Then we can maybe also, and I hope this works a bit faster now, switch on the running motor. So I will open it like this. And now in this sensing voltage source, I have a very small resistance. So it's not blocked, the motor can run. There is no viscous friction, there is just this constant friction. I think on this side nothing changed. I will just run the simulation and for 90 milliseconds, and what we should see is this overshooting effect of the current if the computer is doing something. I think hopefully I've already ordered a new computer in Magdeburg, which should hopefully arrive within the next weeks and which might be a bit faster. So if we take a look at the current, we should see this overshooting that we all know. Okay, and so the next thing that we can maybe have a look at is the characteristic curve of this running motor. This was the thing that was also displayed here in this diagram. And so remember, this is what would not really work in our model that we have built. So yeah, here it would not really work. Just with the viscous friction, you would just get a linear curve. If we add constant friction, like this way, we turn the motor in the opposite direction. So this does the thing that the motor would not turn in the opposite direction. And if we simulate like this, then we should get, now looking at the motor current, now we should see, okay, current is increasing, motor is not turning, right? If we look at the speed at the very same time, not maybe look at the speed because there's much more speed than current there. So it's going up and then we get the flat curve. So if you understand the model properly, why do we get the flat curve now in this case? Here we get, I mean, a steep increase, and then we get something that has a slight increase. Here we only get a steep increase and a perfectly flat increase. So this is the range where the motor is not turning. Here the motor starts to turn, but in this model I only have this constant friction. I don't have friction that depends on velocity. So if we add in this model just another resistor to the mechanical side, put it into the motor and give it this quite small resistance that I've calculated in the table and that we used like 0.1 ohm or so. And if we run again, I think I've done. I think I've way other speeds here, so I think I need to go into the milli range. Okay. Then it's looking good. Maybe even a bit less. I've used other K factors in these examples here. Yeah, so, but then it's fitting quite good. So current increases, then the motor starts to turn, and yeah, and then it turns. The thing is, in our real measurement, we also have kind of an overshooting here, because yeah, there's a friction in the motor that once you hit over the certain amount of friction, then the motor starts to rotate. It's a little bit like a slipping force. Yeah, so you need to be above a certain threshold, and then it will start to rotate, and then the friction gets less once again. And I think this is super difficult to model in the model, because then the motor does not know, do I need to rotate, do I not need to rotate? It's I think very challenging. But I think anyhow, I mean, it's in direct comparison. If I maybe do it like this once again and move my browser window over here, I would say it's not too bad. Okay, so then the last thing is the switching off of the running motor, which is this model here. And this is now even a bit more complicated. So the motor model is the same, but I've really added the switch here. And switches in SPICE and LTspice are also a bit of a challenge, because you have a switch. The switch at the end is just a switched resistance. So when the switch is closed, it means that you have a very small resistance. If you open the switch, it just turns into a very large resistance. And then you need to have another source, another voltage source that controls this switch, or that controls this resistance. So this is the source that controls the switch. This is the switch resistance. And then what is also actually somehow built into the motor is a suppression capacitor. So we have the source, and then we really, like in my, the problem is, let's say if we go back to the model that we have developed, which is, I think, this one, even if I would switch off the source, there could still be a current in this loop. But in my measurement, remember, I really switched off a switch, and I totally stopped and blocked the current. And so therefore, in my model, which is, I think, this one here, I really need to have the switch that switches off the source. Just setting the source to 0 won't do the job, because even if you turn the source to 0, there could still be a current through the source. Okay, so yeah, if we do this, and if we take a look at, I think this was also the point where I measured the voltage, then you see that it's looking quite nicely in a way that we have the 12-volt source voltage, then we switch off, then we get this transient. Yeah, this was really when there was this arc burning in the switch, and the current would go over to this suppression capacitor and so on. But the motor has inertia, and the inertia still keeps the motor rotating and producing some counter electromotive force. And then this counter electromotive force is what we can measure. And then it takes a couple of 100 milliseconds for the motor to turn off. And yeah, so if you compare this with the measurement that we did, which was this diagram, and I will try to put this to the same screen size. Once again, of course, it would be better to have a direct comparison in a certain program, but okay, if I put this, try to put this on the same size, yeah, you can see it's not looking too bad. Yeah, so here we have the source voltage, we switch off, we get this kind of transient, and then the motor is still rotating, acting like a generator, producing this counter electromotive force until the the energy that is stored in the inertia of the motor has gone into friction, and then we just measure 0 voltage. And I think the difference between my measurement here is that this happened here in something like 100 milliseconds, and in my simulation here it takes something like 300 milliseconds. The simulation models, as said, I've created maybe 10 years ago. I would guess that the motor was better at this time. So I remember that it was a better fit, but we could just add more friction, or yeah, if I would, in this model, I only also have this constant friction. If we would add the resistor here, once again for the viscous friction, and set it to 0.1 milli or 0.01 milli and run once again, yeah, it's getting less time. Yeah, so in our model now we have maybe a bit too much of inertia, maybe a bit too few friction to make it fit to the measurement from Saturday. But I would just guess that my motor maybe needs some lubrication. Yeah, I need to have some oil in the motor to make it rotate as good as it rotated 10-15 years ago when I did these initial experiments. Okay. More questions?
One question.
Sure.
We have defined different analysis, and it is executing one of them. Which one? The last one, because we in one particular moment we had the transient and the DC analysis. And the program was running the DC analysis.
Yeah, so because I think now if you have in this model here, maybe let me make this larger once again. So there is still a command for the operating point solution and for the transient analysis, but they are now inserted like a text. So the color of text is blue and the color of real commands is black. So this old command is still there, but it's just inserted as a text, and that's why it's ignored. It's like a comment. Like if you have a Python, or if you have a MATLAB program, and if you have the % sign, let's say this is just ignored. Yeah, it's not really active anymore. More questions?
Do you know if in this program it has limitation in the number of components?
No. There's no limitation in components. There's no limitation. I think at the end, no, nothing. I think it's at the end it's just limited by the memory and computational capacity of your computer. And if you have if you do this transient analysis with lots of elements and lots of nodes, then of course you have you get a big system matrix. And also if you have like power electronic components that are switching fast, like silicon carbide, gallium nitride, MOSFET transistors, then they switch very fast. So you need to have very tiny time steps, and still if you maybe want to simulate a motor, you have stuff that needs milliseconds or seconds to start to rotate to see some effect. And so then you have like nanosecond switching and second of maybe you're checking your control systems at the very same time. And then you need to have, of course, very many of these very tiny time steps. And the LTspice is pretty clever in selecting. So if we go back to the DC thing here, to the transient thing. So you can select some maximum time steps. Still, it will do some automatic time step selection, and it's pretty clever in selecting automatic time steps. So it will notice if you switch something in a circuit, then it will do, if you have fast switching on and off of MOSFETs, let's say, then it will take shorter time steps. And if nothing really happens in the circuit, then it will take longer time steps, go back to the smaller time steps if it's switching, and so on and so on. But still transient simulations of power electronic circuits can be a challenge. Also because you might run into stability problems. so that the circuit does not converge, for example, or the solution does not converge. The where are my slides? Here are my slides. So the maintainer of the LTspice, which is this Mike Engelhardt guy, as mentioned, he has a new project from a company called Corvo, and Corvo does also components, I think also for microwave engineering. And so he is not really, I think, developing this LTspice anymore. He has a new variant which is called QSpice from the Corvo company. We can check in the browser, but I will maybe just switch to my full camera mode for a second. So if we search for QSpice, and if I go back to the screen share, so this is another type of SPICE simulator that is the new project of this Mike Engelhardt. And it's said to be, I don't know, 2 times faster and a couple of times more efficient than this LTspice because it's especially optimized for this type of transient simulations. So if you are starting with something new with power electronic circuits, doing lots of transient analysis, I would recommend maybe to also have a look at this QSpice. It's made the graphical user interface is, from my point of view, not that nice and sophisticated as an LTspice. In an LTspice, you can do more stuff. Yeah, but everything has advantages and disadvantages, let's say.
Okay. And it is possible to use a component from the companies?
And it's possible to use
not only analog devices?
Yeah, also from other components. There's a German company that is very popular called Wirth Electronics. I will once again, I don't want to see all my other stuff here in the browser visible in the things. That's why there's yeah, so this is a filter, for example, that I also where I show demonstrations. When I was in Angers, I were doing stuff with this filter. And so, for example, here for this filter, and for many other components of Wirth Electronic, you will also find LTspice models. And you can download them and use them.
And can you also model your own device? And
you can also model, I mean, we have somehow modeled our own motor right now.
During the pandemic, I simulated it with integrated circuit technology.
Mm-hmm.
I imported the model of the resistor, the machine model. There were some parameters not recognized, but we didn't debug the model. But
okay.
From UNC.
Yeah. So you can just download, unpack, and then you will find them if you put them in the right folder. These components, you will also find them at edit and component, and then they will also somehow show up in this list or in the subfolders that you have there. And there are many other manufacturers who will also offer LTspice models. Okay, so yeah, to sum up, my recommendation, yeah, to avoid this garbage in, garbage out principle that we also have observed, start with simple models and networks that you understand, where you have some idea what should be the output, what I would expect as an output. And if the output is not as you expected, then okay, you might have done a mistake, the simulator might have done a mistake. In most cases, you will have done a mistake. The simulator is in most cases right. Yeah, know what you're doing, question your results, and try to validate your models and results against other tools. So, for example, against the measurement, maybe some analytical formulas, maybe other simulation tools. And yeah, so I know that you're using MATLAB Simulink, for example, which is, from my point of view, pretty nice for control systems. Yeah, and so if you take the very same circuit and try to simulate it from scratch in, let's say, LTspice and MATLAB Simulink, and at the end you get the very same result, of course, it's not a perfect mathematical proof that you have done everything correct, but it would be very, very, very strange if you would have done the very same mistake in both of these simulators, I would guess, right? Okay, so once again, yeah, thanks for attending, and we have time for more questions if you like. I will stand like this, like the squirrel. By the way, if you come to Germany and if you want to practice German, this is probably for foreigners one of the most complicated words. How this animal is called in Germany? It's called Eichhörnchen. Eichhörnchen. So Eiche is a tree like the oak, and Hörnchen is also always, if a word is ending in chen, it means it's something small, and so it's a small animal that lives on the oak tree. This is literally what Eichhörnchen would translate to. Okay, thank you.
Okay, thank you.